Welcome back. So, in continuation with the previous lecture, wherein we have come across binary addition, and we are yet to continue with the adders, right? So, today we will see adders. So, we have seen addition, how to do a binary addition in the previous lecture, like how to carry forward a particular bit and accordingly what does happen as an adder, right? So, there are different types of adders. So combinational logic circuit that performs the addition of two single bits. Two single bit is called as a half adder. Yeah. If it is going to perform the addition of three single bits, it is called as a full adder. Now what is two single bit and three single bit? Two single bits are the inputs, because as long as we do not have two numbers, we cannot do an addition. Same is the case here. We need to have two single bits, then we do a normal addition. Now what will happen if a carry is generated? Like in a normal decimal number addition, how do we do? A 9 plus 8 is 17. You write a 7 and 1 you carry forward it, right? You write a 7 and 1 you carry forward it. Now what we will do with that 1? We add it with the previous number. That's how we do. Now what is the provision here given in case of these digital logic circuits is you have two bits for addition, and in case you get a carry, that becomes the third bit, which actually we have to follow the regular procedure of adding it with the next number, and such a case is called as a full adder. So in the earlier case, that is half adder, we don't do anything with the carry. Yeah, if at all it is a carry, then it is called as a full adder. So the carry is to be carried forwarded to the next number, and accordingly it is to be added. So these are the two different types of adder. The first one being a half adder and the second one is a full adder. Now what's exactly a half adder? So it's nothing but a logic device that's going to add two binary numbers. It will only add the least significant digits column, that is ones column in binary addition. Only the least one bit addition it's going to do. So if you are considering the half adder, it's a box with two inputs as in it is bits, one bit. Yeah. Then output will be, we get the sum and then the carry also. Suppose you give a 1 and a 0. 1 plus 0 is a 1 and the carry will be 0. If suppose I am going to take an input as a 1 and a 1, what will do? 1 and a 1, output will be a 0 but carry is 1. It goes like this. This is how it happens. Now what could be the logic diagram? So we know we have actually the case here is it's going to add it and it's going to give the carry. That's the case in this case. Now what will happen if A is a 0, B is a 0, the sum is a 0, carry is a 0. A, these are A, B, the sum and a carry. So this is the truth table. A 0, 0 will give you a 0, 0. A 0 and a 1 will give a 1 and a 0. A 1 and a 0 input will give us a 1 and a 0. But a 1 and a 1 will give a 0 and a carry 1. Now if you look at this particular truth table, the sum circuit alone, the sum truth table alone gives the behavior of an XOR gate, and hence an XOR gate is drawn here. So it gives, because even if there is a change in one bit, the output will go as a 1. That's the explanation of an XOR gate. Now if so, this is nothing but your XOR gate, and hence A and B, for the sum output, it is given to an XOR gate. So when you look at the truth table of AB along with the carry, it gives an AND gate and truth table output. Yeah, this gives an AND truth table output. So this goes like this. This is what we are considering, which is nothing but the AND gate, and hence to the A and B we give an AND gate. So if you look at a circuit of a half adder, it is a combination of an XOR and an AND gate. So this is called as the logic diagram. This is the logic diagram of a half adder. Yeah. So S is equal to A XORed with B and C is equal to A into B. Now what is a full adder? As I mentioned, for a full adder, it is 3 bits. The carry is also, even if a carry is 0, we keep adding that carry 0 to the next number. That's how it is, right? So a combinational circuit that adds 3 input bits to generate a sum bit and a carry bit is called as a full adder. Now, we have seen what is a min term and what is a max term. So this is how we represent a min term. This means where 3 will have a value 1. Yeah, 3 will have a value 1. 5 will have a value 1, 6 will have a value 1 and 7 will have a value 1. That is for the carry. So in case of a sum, what is it? In sum, 1 will have a value 1, 2 is having, 4 has and 7 has, and hence we are writing it. This also we have seen in the previous lecture, right? How to write the min term. Wherever the output goes 1, those input terms we have to consider. That is how it is, right? So how did we write it is what is given here. Now, so this is the truth table, we know, right? So 3-bit addition, one of them is considered to be the carry. This is a full adder. So when we are going to consider this as the case, what will be the sum? 0 plus 0 plus 0 is a 0. 0 plus 0 plus 1 is a 1. 0, 1, 0 is 1. 0 and a 1 and a 1 will become a 0 with a carry 1. 1 plus 1 plus 1 will be a 1 and a carry 1. That's how it works. That's how it is formed. Same, so that's how we have the carry like this, right? Now, these are the min terms as I said. Now, what is a full adder? I mean, we have taken an example in such a way that we can, simplify the terms in order to come up with the logic diagram, right? We all know by now, like how to simplify the given truth table. How do we simplify? We are expected to place them in the K-map. So we have seen K-map examples also. So for a sum we need, so for if we have more than one output, so many K-maps we are expected to make it, right? So there are 2 outputs. For sum we will make one K-map. For carry we are going to make a K-map. So we will just consider the sum case here. It is 3 input. X and Y Z, you can keep it, or you can keep X here and a Y Z here. It is all the way right. Or X, Y here and Y, Z here. It is all right. Now we have considered X and Y, Z. So we know it is 0, 0, 0, 1, 1, 1 and a 1, 0. Why it is 1, 1 and a 0? That also has been discussed. There should be only 1 bit change. Right? There should be only 1 bit change. So whichever min term is having a 1, we are marking it. So here if you see for the sum, this 1 is having a min term. Then 2 has a min term. Then 4 has a min term, and then the last min term is 7. So over there we have placed all these ones. Now we are just going to look into it whether we can pair them as per the rules we have seen. No, we cannot pair it anyone. They are not in the corners. They are not together. We cannot do it anyway diagonally. Yeah, diagonally will it work? No. The rule is we should not pair them diagonally. Even though they are present diagonally, we cannot pair them diagonally. Right? So that pairing is going to be wrong. So what will happen in that case? We are expected to write the complete set. Like this is nothing but your x dash. The first one is x dash. Why x dash? That is x bar, because x is equal to 0. Y bar and 1. So x dash y dash z. The next one x dash y z dash. The next one x y dash z dash, then x y z. We have written the complete, and then we are trying to simplify using the Boolean laws, right? After writing the K-map, you are not able to pair it, then we are trying to simplify them with the Boolean. So pairing them accordingly, splitting it, making it use of an associative law, then we come across that we get x XOR y XOR z. This is how we get, because we take out the common terms here. This common terms we are taking it out. This is nothing but y dash z plus y z dash is nothing but y XOR z. Similarly here this is y XOR x nor y x nor. This is x nor. This is y x nor. This is XOR. Okay, this is XOR. So we are again trying to combine x with this, and then we finally get it XOR Y XOR Z. Similarly, for a carry, if you see, we are just going to place it, but we see that we can pair them. Accordingly, we are just pairing them. Finally, the equation says C is equal to, what is it being paired accordingly? XY plus YZ plus ZX. This would be the equation after pairing. Yeah, so we have already seen how to reduce the equation after pairing, and this is how we have to do it. So this is a full adder equation. So in short, if you see, this is the equation of a full adder and this is the equation of a half adder. So full adder is equal to two half adders. It's a combination of two half adders is called as the full adder. Now how it is, we are getting it as a 2, we are just trying to find out by using the Boolean's law, right? So sum is equal to xy plus xz plus yz, and then how we are framing it, you can just go through it. And hence finally if you see, one full adder is a combination of two half adders. Now here Z is considered as C, that is the carry in. Yeah, this is how we redraw a full adder. So what is a full adder? Binary equation, sorry, logic symbol we will see. This is a full adder and this is going to be a circuit diagram. Yeah, these are nothing but two half adders. Two half adders. So how do we build an adder for n-bit numbers? Whatever we are talking is all about 2-bit number and a 3-bit number. If it is more than 3-bit number, how can we do that? Like for example, if you are asked a question, how do you build a 4-bit adder? How many inputs are there? So the consideration is how many inputs are there? How many outputs are there? What will be the size of the truth table? How many functions will it have? All these things comes in mind, right? 4-bit adder. Now how is it going to add? Like we know for 2-bit addition, 3-bit addition, we have been looking at half adders and full adders. Now the question is what if they are bigger adders? What do you mean by bigger adders? If it is more than 2 bits, more than 3 bits, what am I going to do? So far we have been seeing only 1 bit, right? 1-bit addition. A and B will have a 1 bit. Like A and B will have one bit. So we kept on adding that. But when it is 4 bits, it means A will have 4 bits separately, B will have 4 bits separately, and that addition we have to take. So if you see how many inputs are there, 4 plus 4, 8, and a carry. We'll have a 9 inputs. What are the possible outputs? 4 sum outputs we will get and 1 final carry we will get. So it is 5 outputs. What will be the size of the truth table? The way we start 0, 0, 0, 0, it has to go till 1, 1, 1, 1. Yeah. Likewise, this will have a separate 15 combinations against the 0, 0 combination of B. So if you look into the truth table is going to be huge with 512 rows. And how many functions will be there? The functions will be 5, 4 for the sum and 1 for the carry. So this is how we have to do for bigger additions. So however big the numbers are, the logic remains the same. We are going to use a full adder for addition. Why full adder? Because its own bits as inputs and a carry from the previous bit. And these are all there for the bigger adders. Right? So any number of bits can have a addition operation. Thank you.